In conventional wireless reception and transmission approaches, the transmitter simply broadcasts the signal in all directions to serve the user. This is an inefficient approach due to the finite transmitted power and the interference caused by signals serving other users. A more efficient approach is to utilize beamforming. Beamforming can also be applied to cleverly mitigate multipath, enabling precise indoor localization. It is known that the precision achieved from time of arrival based localization is superior to other radio localization approaches. LTE signals in indoor environments experience short multipath delays, which induces significant localization errors when using time of arrival based localization. This video demonstrates how beamforming can be applied to mitigate multipath for time of arrival based indoor localization with LTE signals. Using beamforming, spatial discrimination captures the line of sight signal and nulls the multipath components as much as possible. This refines the time of arrival estimates and compensates for multipath induced biases. For spatial discrimination, we typically need a large aperture or multiple antenna elements, which is impractical in many applications. Instead, we can use synthetic aperture by exploiting the antenna motion, capturing signals from a moving single element antenna at different instances. Measurements taken at different time instants correspond to different antenna positions. In this work, a synthetic aperture-based beamforming framework is developed and integrated with an LTE receiver to localize users indoors to an unprecedented degree of accuracy. In this framework, the LTE receiver samples signals from the moving antenna and tracks the cell-specific reference signal. The resulting channel impulse responses are stacked and passed towards the beamforming block to estimate the number of incoming signals. Then, the estimation of signals parameters via rotational invariance techniques algorithm is applied to estimate the direction of arrival of the incoming signals and detect the line of sight path. After estimating the line of sight direction of arrival, the received signals are beamformed towards the line of sight path while suppressing the multipath components. The beamformed data is processed and the corrected carrier phase measurements are fed back to the LTE receiver, which refines the navigation observables that are subsequently sent to an extended Kalman filter to estimate the pedestrian-mounted receiver position and velocity, along with the clock biases of the receiver and LTE transmitters. To validate the proposed approach, an experiment was performed in the Engineering Gateway building at the University of California, Irvine. The LTE receiver was listening to 6 LTE towers, also known as eNode Bs, from 3 US cellular providers transmitting at 4 different carrier frequencies. A quad-channel National Instrument Universal Software Radio Peripheral 2955 was connected to the pedestrian-mounted receiver to sample LTE signals with a sampling rate of 10 megasamples per second. The receiver was equipped with 4 consumer-grade cellular omnidirectional layered antennas. The top right window shows the pedestrian walking in the building. The bottom right window shows the pedestrian ground truth trajectory and the estimated trajectory produced by our framework. The top left window is showing the spatial power spectrum of one eNode B at a time using different direction of arrival estimators. The multiple peaks represent the line of sight and/or multipath components. Also, it shows the number of incoming signals. The bottom left window shows the true direction of arrival of the line of sight component in solid lines for each eNode bead, and the dashed lines dancing around the solid lines are the estimates. The ground truth was obtained with a camera that was mounted on the moving cart, which was pushed by the pedestrian to record the location of specific landmarks in the environment with known locations. Throughout the entire experiment, the receiver traversed a distance of 126 meters in 100 seconds. This top view of the results shows the performance of a standalone LTE receiver in white and the proposed LTE synthetic aperture approach in green versus the ground truth in red. The position root mean squared error of the standalone LTE receiver is 7.19 meters. Here, a standalone LTE solution means that the LTE did not use a synthetic aperture-based spatial discrimination. By including the proposed framework, the error was reduced to 3.93 meters.